Hello, I'm Dr. Patricia Shaw, and welcome to the seventh and final video on robotics programming with Robot Benchmark. In this video, we'll be having a look at the wall following challenge and why it's so important for robotics. So this particular challenge, it gives you a Pioneer robot which has two-wheel differential drive, and the challenge is to follow a randomly generated wall at a predefined set distance for 1 minute. The Pioneer robot has got a total of 16 sonar sensors, 8 mounted around the front and 8 around the rear. And we'll have a closer look at this robot in a moment. But first of all, why is wall following so important? Well, robot wall following is actually a very common strategy for enabling robots to be able to navigate around unknown environments. If we have a complete map of an environment, or we're out and about using our choice of maps like Google Maps or OpenStreetMaps, then it might be seen as having a global knowledge of the environment that we want to traverse across. And then we can plan a route, or the maps can generate a route for us across that environment, taking into account the known paths and obstacles in that environment. But sometimes we only have local knowledge, and local knowledge is essentially limited to what we can currently perceive. And so in the case of a robot might gradually build up a global map by combining together lots of samples over a period of time. But as it's traversing through a map, it also has to adjust what it's doing in response to what it's actually perceiving. And this enables it to react to changes from what it previously perceived. For example, a person walking across the path or a new obstacle appearing that needs to be accounted for. But in the early days of robotics, then we didn't necessarily have these global maps or the ability to build them. But we did have local knowledge from the sensors, and we were able to use that quite reliably to be able to build up path planning algorithms. And there's a set of these called bug algorithms. I'm not going to go into a huge amount of detail about those, but essentially they're a whole series of algorithms that builds up in complexity that defines how you can start from go from a starting location to a goal location, traveling in a straight line as much as possible towards that goal location, but navigating, following along any walls of obstacles that are encountered as you go. And that will eventually get you to the target location. As you go up the different levels of the bug algorithm, they get increasingly sophisticated and need to remember more and more about the environment in order to be able to complete this navigation. But that's as much as I'll go into about bug algorithms. What I instead want to talk about today is what are these sonar sensors and how do they work? Because actually understanding the sensors that we're using to perceive the environment is really important. Being aware of what their limitations are and what the information is that they're actually giving us can make a big difference when we're trying to develop an application that makes use of that sensor information. So the Pioneer robot is giving us a sonar sensor. And specifically, sonar actually used to be an acronym. Well, it is an acronym, but it's not tend to refer to it by its acronym anymore. But it did stand for Sound Navigation and Ranging. And that essentially covers a whole range of sound frequencies, from very low frequency that might be used underwater. And we can often see, or there's various sea creatures such as whales that do make use of sonar, low frequency sonar, for communicating over a very long distance. And of course, submarines use this as a way of detecting obstacles underwater as well. At the other end of the sound frequency, we have very high frequency, and this tends to be above a frequency that we're actually even able to hear. And that's where we're using sound and bouncing that off, and that tends to be above ground, detecting obstacles. And in the animal kingdom, again, it's used by bats for their vision. Their eyes aren't particularly good, but they're incredibly good at utilizing these ultrasonic frequencies in order to be able to detect obstacles and also their prey. Another example of using ultrasonics that you might have come across is car parking sensors, where they have little sensors around the car bumpers that beep when you get really close to obstacles. They're using ultrasonic sensors as well. So although we're calling them sonar sensors on the Pioneer, they are actually ultrasonic sensors that we are using. So how do they work? Well, we have the ultrasonic sensor, and you'll often see two sort of circles next to each other that look like miniature speakers. And one of those will be emitting sound outwards. So it will broadcast the sound so high frequency you can't actually hear it, but there will be sound waves propagating out. When those sound waves hit an obstacle, then that sound is actually reflected back. And the second of those ultrasonic speakers is actually able to detect the sound that is reflected back. Now, because this type of sensor is having to send out a signal in order to be able to get a response back, we actually call it an active sensor. And that might be different from, say, a light sensor that is just passively receiving light, and that light is adjusting how much resistance it's giving within a circuit. So an ultrasonic sensor is actually an active sensor that is having to send out a signal in order to be able to receive sensor information back. So what are the limitations of these sensors? So it's worthwhile being aware of how this works. So we know we're sending out a sound wave, and that's going to bounce back from the objects. But typically with these sound waves, we're sending it out in a cone shape. And that, when we get a signal coming back from it, it'll typically tell us about the first object it actually encounters. But it won't necessarily tell us which direction that sound wave has come from, only that it's received a signal that has come back from the signal that it sent out. So in this particular example, we would get a signal back that would come from the bottom object because that's the closest, but we wouldn't know whereabouts in this cone it had actually come from, or that there were actually three separate objects there that it could potentially have detected. In a more sophisticated ultrasonic sensor, then you might get a bit more information back, or you might hear the delayed additional signals bouncing back from the second two objects. But in most cases, we'll only get that first message bouncing back. The other limitation of a sonar sensor is the angle at which it's sending out. So we're sending it out in this cone. It's coming out from the sonar. But if if the signal that it's bouncing back from is if the angle of that signal is too far around, so we're sort of bouncing off at a very shallow angle, then essentially we won't receive that signal. We'll miss the receiver on the way back because it will be bouncing off at a different angle. So we actually need to be relatively straight on to the obstacle that we're trying to detect. And we have this sort of 45-degree angle that we can actually still just about receive signals from. So we can be at most 45 degrees to the surface of the object that we're interested in order to be able to detect it. So how does that link into the Pioneer robot that we're trying to drive? Well, the Pioneer robot, as I say, has got 8 sensors at the front and 8 at the back. These sensors are arranged in sort of an arc around the front and the rear. And interestingly, these front sensors, these sensors are angled at 20 degrees to each other. So that means that we've got a pretty high confidence that when we send out a signal from one of these, we're likely to get a signal coming back to that same sensor for most of the wall that we're going to be trying to follow. The very side sensors are actually at 40 degrees, but for the remainder, then we should get at least 1, hopefully 2, most of the time, giving us a signal back. And clearly how the particular sensor that's giving us those signals can adjust how much we decide we need to turn by in order to drive the robot. So before we have a look at tackling the challenge, let's go over and have a look at the robot benchmark. I should say in the instructions, it does give you a bit more information about the sonars and the angles of incidence for obtaining that sonar information back, and the particular challenge that we're trying to do. So if I expand this window slightly, we can see it's generating a random wall here, and we're required to travel, maintain a distance of 50 centimeters from that wall as much as possible. And when it generates that wall, it generates the optimal route, and it basically compares your route against that optimal route. And so your performance is how well you match that route. If we have a look at the environment, if I zoom out here a moment, then you can see the wall that it has generated there. Remember how to, there we go. We can see the wall that is generated for us to try and follow. So there's some quite tight corners in there, both in and out, and traveling for quite a distance. After we reach a minute, then the simulation will stop. And so that will give us the score. If we load up the program for this, then we have a function that will give us the sonar distance. We'll actually convert it into a value in meters for us. So we've got this get distance that will take the sonar sensor reading and convert it into distance and read it meters for us. We've got the usual bits of importing the robot, setting the time step, connecting to the motors, changing them to velocity control mode from position mode. And then here we're getting access to those distance sensors. Now, the initial program only gives you 2 of those sensors, but clearly you could also gain access to more of those. And you might find it useful to pop those into an array rather than having lots of variables, but that's up to you. We're told the maximum speed that this robot can travel at is 5.24. And they use that maximum speed to start the robot driving. Now we have this initial loop that will essentially enable the robot to get from its initial starting point up to parallel to the wall and then start to follow the wall. So at that point, it will then rotate until it is side on to the wall. And at this stage, this is where the actual wall following begins. So they're getting the distance from the side sensor, and then they're using that to adjust the velocities accordingly. So let's have a think about some strategies. I'll just quickly show that running. So you can see it starts off driving to the wall in a straight line. This is the first part of the challenge. We then side on to the wall, and at this point it starts to try and follow that, but we have a very simple controller at the moment that's not necessarily as effective, and we need to improve that control. You can see the performance clocking up here, but actually the robot gets stuck quite quickly. So let's go and think about how we can actually have a go at tackling this challenge. So we've got various different sensors on the robot. We've got some at the front and some at the rear. If we want to know if we're parallel to the wall, then using the front and rear sensors would enable us to evaluate that to try and work out if we are actually currently parallel at the right distance. So adding in that rear sensor, side-on sensor might be a useful starting point to try and at least get that parallel behavior working correctly. Once you then have that, then you still want to start looking at the additional sensors in order to be able to detect the upcoming changes in the wall. So you can think about how much you perhaps want to turn based on which sensors it is that's actively detecting something in the upcoming wall. And of course, if none of the sensors can detect anything, then the chances are there's been a sharp bend taking the wall away from you, so you need to actually turn back towards that. The other thing you might want to adjust is also the velocity at which you're traveling. So clearly for actually turning, they are making some adjustments, but they're using some hard-coded values in there. What you could consider doing instead is taking those distances in front of you that you're able to detect and confident that you're traveling at the right speed in order to be able to adjust your velocities. If you're sensing the wall approaching in front of you, then you possibly want to slow down so you can have a bit more control going around and following that new angles of the wall. It might take a little bit longer, but you may well find you get further as a result of it, or at least with a higher accuracy, by taking a bit more time and traveling more slowly when you are trying to adjust to the wall, changes in angle against the wall. So there we have it. And just to say, so this is the final video in this series that we're looking at for the robot benchmark challenges. But if you do want to continue on, there are 4 more challenges on the robot benchmark still available. I should say that the complexity of these challenges does jump up significantly. But if you're interested in continuing with learning about robots, there are various online tutorials and courses that you can take in order to find out some more. Or you could actually have a look more closely at the WebBot Simulator, which is essentially what we've been using through the robot benchmark. The WebBot Simulator is available and free to download. It does work on various different platforms, so hopefully you are able to run it, and it is free as well for individual use on your own computer. So you can potentially download that, and it's got examples of environments and robots that you can load into it and start to build up programs. Of course, you can take in some of the programs from the robot benchmark because they are using the same language in order to be able to program those and build up some more sophisticated robot applications. And then as you develop, you could perhaps even develop your own environments and robots to operate in those environments. So I hope you enjoyed it and found that this series of videos informative, and best wishes with the challenges.